Hello, my name is Antonio. I work at IBM Quantum. I'm the head of Quantum and HPC integration. And the topic of today's session is workflows for quantum-centric supercomputing. The idea, high level, is to give you some idea of how the next evolution of computing is going to come to be, and how quantum computing will play an essential part there, and to get some intuition about how the workflows for that kind of computations are going to be evolving. I will start very briefly by pointing out why do we use computers. And in order to do that, what I've done is a very fun exercise where I took a 5x5 matrix and calculated the determinant by hand. This is something I had not done before, but most of us have done something similar as part of our education by doing smaller determinants, like 4x4, for example. So in this case, I ran this, I calculated this determinant by hand, and it took me about 1 hour and a half, 1 hour and 27 minutes. And I got this result that we have there at the bottom right of this page. And then I went ahead and calculated this with NumPy, which is a package in Python to do several mathematical operations and calculate this determinant. And it took a few hundred microseconds, so it was several tens of millions faster than I accomplished by hand. And it gave me an answer that was slightly different than mine. Obviously, I trust the answer given by the computer much more than I would trust my own answer. And this is one of the reasons that we will say, oh, why do we use computers? Well, they are faster, they are incredibly faster, and they are more reliable in terms of accuracy. In fact, I will say I could have been a lot faster doing my 5x5 determinant. I could have calculated that in a single second, but the accuracy will have suffered a lot, and probably I would have been nowhere near the final result. So there is that trade-off. One important point is that you can scale the size of your problem typically for computers without sacrificing accuracy. So now if I go and I say I'm going to do a matrix with 1 billion elements inside, and I can try to calculate the determinant, now we can increase the size of the problem, typically with computers, without sacrificing accuracy. And in this case, I could say, well, I could do the same computation. I can compute the determinant for a matrix that is a lot bigger, like 1 billion terms inside. And I wouldn't expect the accuracy to suffer as a result. I'm not going to go through the exercise myself of doing that by hand, but I could trust that computation to a computer, and I will feel fairly confident that the result will be as accurate as my 5x5 result. So, of course, we use computers for many other things that calculate indeterminants, and you will use computers in your day life for a variety of things, like checking flight ticket prices or checking the state of the stock market or something like that. But we can rely on them for this kind of very large operations that require accuracy at speed. Now, to take a step back, we can ask ourselves, what is computing? And the most intuitive way of thinking about this is going back to the Turing machine and that model that requires that a computer has some initial state that goes through a series of operations, and there is a mechanism to extract information from that machine. This sequence of operations has to be finite, and that is something very important because it separates what is computable from what is not computable. Being finite doesn't mean that it's going to be short. It could be a very, 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 very long computation, but we can be guaranteed that if the sequence of operations is finite, we are going to reach a final result. Now, once we define what is computing, typically the everyday computers that we use in our everyday life can do a lot of things for us, but they are not enough for some very large scale computations. And so this is how this field of high performance computing has come to be. There are 3 ingredients in what we call HPC or supercomputing. One of them is making these computations parallel, massively parallel, so you can rather than going sequentially into an instruction and a result, an instruction and a result, you can parallelize this task. You can then deliver this parallelized task to some hardware that is going to be arranged in some sort of clusters of computing resources. And these clusters will be connected through a network, typically very high speed, and they will have access to memory, very, very fast access to memory that supports these computations in a parallelized way. And these components are high performance, meaning that they can do operations at a very fast rate, and they can move data at a very fast rate. So this high performance computing that has been developed for a few decades now, it really constitutes a state of the art in what we understand as computing. And you probably have heard about Moore's law that determines the doubling on computing power every couple of years without the increase in cost, and how that has been slowing down, and it will eventually be meeting a limit imposed by our ability to fabricate smaller and smaller pieces of hardware. One thing that's important about quantum computing, and I will talk about quantum computing a little bit in a minute, is that it's not really the evolution of what is after Moore's law. It's a branching in a computing paradigm. Quantum computing will allow us to perform some calculations that will be outside of our reach, even with the normal evolution of Moore's law. It's really a branching in compute, and it's the only branching that we will ever have. So the development of quantum computers will constitute a really important point in history in terms of computing, and it will bring the next generation of really high performance computing. To go a little bit into what is quantum, and you probably have been going through this in part of the school, there are a couple of ingredients that go into what we were talking about for the Turing model. And these 2 points are really critical in the way that quantum information is processed. One point is that a physical system can be in a perfectly defined state and can still behave randomly. You hear this effect normally as quantum superposition. I like to describe it this way. It doesn't have any math, and it has a statement that seems and sounds challenging. Something can be perfectly definite and behave randomly. But that's what quantum superposition does. And the second part, which is related to entanglement, is that two systems can be very, very far apart, so far that they cannot influence each other. And yet there can be correlations between them that are very, very strong, stronger than what you could explain classically. These two pieces are essential for quantum computing, but we need also the set of instructions. We need the algorithm, because we are saying that the system will behave randomly, but we want to have an answer at the end of our algorithm that is not random. We want to have an answer that is the answer to the computational problem we are looking for. And that's what the quantum algorithm is designed for, to drive the probability distribution that is going to be the outcome of the measurement of our quantum system, to have it being progressively more concentrated around the answer that the algorithm is going to provide. So that it's so concentrated at the end that we will have a measurement of the right answer with very high probability. The idea of quantum computer was initially proposed by Richard Feynman in the 70s, 80s, and things have evolved a lot since in terms of both hardware and also algorithm development. And we will talk a little bit about that later during the session. So now we have HPC, we have quantum computing, and now I wanted to use kind of like a guide for writing workflows to take advantage of quantum computing. You could think about this as some sort of quantum programming model. And this is what we call Qiskit patterns. So Qiskit patterns are these guides for writing workflows, in fact, that are divided in several steps. And the most natural way of breaking that down is to imagine a first step that is a pre-processing step, an execution step where you use quantum hardware to deal with quantum information, and then you'll have a post-processing step. This pre-processing can be divided in some other steps, and here we have 4. 2 of them are pre-processing, then we have the execution, and we have the post-processing at the end. The pre-processing can be thought as a mapping step where you take the computational problem that you want to solve and translate it into the fundamental unit for quantum information processing, which is a quantum circuit. Then once you have that quantum circuit, you want to optimize it and run some steps that we call transpiling to turn it into something that is executable by our quantum hardware. Then this is sent to the machine, is executed in quantum hardware, and then you get an outcome, which is either bit strings or a probability distribution. And there we have a post-processing step, which is going to take that outcome and is going to transform it into some domain-specific answer. For example, if you are calculating the energy of a molecule, it will take some output in terms of bit strings or expectation values, or probability distribution, and turn it into expectation value, which gives you the energy. Each of these 4 steps, very importantly, is amenable to be parallelized. And that ties back with what I was saying about HPC and the way that we acquire the ability to run things much more performant and with higher speeds by parallelizing the workflows. So here we can do that in the classical step for pre-processing. We can also parallelize the execution, and we can parallelize the post-processing, which again is a classical step. And it all comes together in this vision that we have about quantum-centric supercomputing, which is resources that are both classical and quantum working together in parallelized workloads to run computations beyond what has been possible before with only classical. You can think about how the quantum part, which we call QPU for quantum processing unit, will enter this picture if you think about what is hard for some problems that quantum can tackle. And the hard part tends to be the correlation between data. When the correlation is very complex, it's very hard to design classical algorithms that will deal with those correlations efficiently. But there are quantum algorithms that can do that for certain type of problems. Normally you can think of CPUs as something doing like scalar functions, and GPUs, which is an accelerator at tackling like kind of vector functions. For QPU, we'll think that they are tackling the correlations in the problem. And that's how all these pieces could come together in a workflow for this kind of paradigm for quantum-centric supercomputing. The pieces we can define in terms of like a quantum computer, which we have in this box, and it has at the core what we call a QPU, which is a quantum processing unit. And that includes all the elements that are responsible for accepting and executing a quantum circuit and providing an accurate result. That includes the quantum chip, that includes all the elements inside the fridge that allow the quantum chip to perform, including the amplifiers and the filtering, etc. We also have the control electronics to provide the pulses that are going to implement the circuits. And we have things like also the coding for error correction in the future. We'll have the measurement discrimination. We'll have all the classical compute that is responsible for holding the waveforms and so on. So that will be the QPU. And then the quantum computer has the QPU, and then it has all the classical compute that hosts the runtime environment, which in our case is the Qiskit runtime primitive service. Right? And this infrastructure will perform tasks like doing the error mitigation for the primitives, calibration, and having a storage for the calibrations and things like that. This will be what we define as our quantum computer, and this quantum computer will be accepting inputs that are in the form of quantum circuits of a very particular form. These quantum circuits will have already the topology inherent to the device, and they will contain only the gates that our device can execute. And also it will have, as part of that input, the set of operators that we want to get the expectation value out of. And then we'll have an output that is in terms of either samples or observables. Now, this quantum computer, now we can imagine, is part of something else, which we call a quantum-centric supercomputer. And this is a system that will orchestrate classical and quantum resources in an efficient way, and it will potentially leverage high bandwidth connectivity between the classical and the quantum, but also it can have as a concept broader implications in the sense that we can imagine this integration to be not tight, to be loose, and having the quantum computer living elsewhere, not in the same data center, and being accessible through the cloud, as we have here in this diagram. So all these kind of integrations are possible. Some problems will not require a tight integration. Some problems might require a tight integration. And we will be seeing a little bit of some example of a tight integration later on in the session. Okay, so when we think about this kind of system architecture, we can imagine that we will have a data center with which will have some classical compute resources, and the same way that we will have, for example, GPUs plugged into some nodes for our clusters. We can imagine that we will have some elements in some of the nodes that have privileged communication with our quantum computer. This is what we are labeling here as virtual QPU, because we are not going to plug our quantum computer into a classical node, because our quantum computers by design these days are systems that are very large. What we can have is we can have this virtual QPU element in our node that will communicate with our quantum computer, and our quantum computer will only accept instructions from that virtual QPU. And here at the top, you can see some blow up of some of the nodes within the cluster, including a quantum element, which is a quantum computer that can be either collocated or remote. And we can see how a workload manager, which is very ubiquitous in HPC these days, can also be extended in capabilities to handle calls to the quantum computer. And we could have this workflow where we have in blue here some of the elements, or all the elements of the Qiskit pattern, where we'll have a mapping, a step that is done physically at the classical node, an optimization step that is also done at the physical node. And then the execution is diverted to the quantum computer. We'll get the answer back. And then we'll have the post-process step also at the classical node, and then that will be in sync with the workload manager, which will assign resources as they are needed and according to the availability of these resources. So this is kind of the view of how these things will come to be. There is layers of software that I'm not going to get into that need to get developed, and there are infrastructure advances that also need to happen for the hardware integration to also work for these kind of architectures. But that's not part of what I will talk about today. I want to now go into another part, which is what we call circuit knitting. And this is very important and related to what I was talking about, because circuit knitting is essentially a protocol by which we take a quantum computational problem, which you can define as one circuit and one observable, let's say one polygroup, and then you can break it down into multiple quantum circuits and multiple observables, or multiple quantum computational problems. You can execute all those multiple quantum computational problems in parallel, and then have the output back to you and assemble the results into a final answer, which is the answer to the original quantum computational problem. So this goes very well with what we were talking before about parallelizing workloads. There are several examples of circuit knitting today. There will be more that are developed, I'm sure, in the future, but I will go through 6 of them in particular. And some of those, if you have been following the literature, you might recall that some of those refer to what initially was circuit knitting, which basically it consisted of breaking down circuits into smaller circuits for easier execution. Now, the point on the new definition is that the breakdown of the problem happens not only at the circuit level, it can happen at the algorithm level. Typically, when you have a breakdown at the circuit level in several circuits, you tend to pay an exponential price on it, exponentially in the number of break-ins that you do in the circuit. Or every time you look inside a quantum circuit and you look with classical eyes, you are going to pay a price that is exponential on the size of the area you are looking at. So not all of these examples that I'm showing here have that exponential price, and that's very interesting, but some of them do. So I will go in order. I will look at embedding, circuit cutting, entanglement forging, operator backpropagation, then a new version of Shor's algorithm for factoring, and something called multi-product formulas. To start with embedding, I will give a very, very brief overview of variational quantum eigensolver, which is a protocol to solve typically the solution to some Hamiltonians in a variational way. And the way this works is you will take a Hamiltonian, you break it down in components that are in terms of Pauli elements, like in this example here. And then the goal is to find the wave function that minimizes the expectation value of that Hamiltonian, because that tends to be the energy if that Hamiltonian represents, for example, a molecule or something like that. So now the variational parts come from the fact that you parameterize the circuit that implements this wave function psi. And then what you do is you do an iteration of preparing that state and then getting the expectation value by measuring all those Pauli terms at the output of your circuit. And then you get that output number to an optimizer, which is going to come up with a new set of parameters with the aim at minimizing that output. And eventually you will see all that decaying, and then it will converge to some minimum value. And that is the answer to your problem. Typically, getting the circuit that implements psi very well is very hard. It's one of the hardest things of this VQE protocol, because it's not obvious how to capture, to implement an eigenstate of the Hamiltonian that you want to solve. And there are methods that approximate you there really, really well, but they tend to be very expensive in terms of circuit size. So you need very, very, very large circuits. So what people tend to do is to come to a compromise and say, well, maybe I'm not implementing the eigenstate I want very well, but I can do it with a circuit that is a lot cheaper. Now, once we have this variational quantum eigensolver in place, this embedding protocol, what it aims at doing is it's taking, this is aimed at solving problems about electronic structure in molecules. So this embedding protocol, it identifies spaces in your problem where the correlations are low, and then tackles that classically. And then where the correlations are high, it identifies some subset of orbitals where the correlations are high. And that is passed on to the quantum computer to be solved, for example, by VQE. And what you can do with that is you can reduce your overhead by reducing the amount of orbitals that you are dealing with in the classical and in the quantum, and just sending the complicated part to the quantum in order to solve it a bit more efficiently. And you end up with this kind of nested loop protocol where you will have an initial guess for your ansatz or your eigenstate, or the circuit that implements the eigenstate as a result of the initial classical computation that we call here DFT for density functional theory. And once we have that output, then what we do is we run a loop for the VQE protocol. Once that energy converges, we pass that energy to the classical again, and we compute the entire energy of the molecule, and then we do a new iteration with a new ansatz and so on. With a little bit more detail, we can see how we can break down the problem into what is called active space, where the correlations are larger, and inactive space in terms of like fully occupied active space and empty, fully occupied inactive space and an empty inactive space. And this fully occupied inactive space ends up being like a mean field perturbation to the VQE part. And now we have this answer that goes into the quantum computer, and then we have the VQE protocol, and whose output then is plugged in the classical loop again. Here are a few papers that describe this protocol in more detail, but if you think about this workflow as something that is trying to leverage classical compute capabilities that we can use to tackle the low correlation inactive space part of the problem, and the quantum part that is doing the kind of like the heavy lift for the complexity of the problem. Then this fits very well into this vision of quantum-centric supercomputing. We can also parallelize a lot of these computational tasks. For example, the VQE, you could essentially run the circuit for with the same circuit but with different kind of observables at the end of it, and run those in parallel. Now, you have to be careful that today the different physical QPU, the quantum hardware tends to be very different from each other in terms of noise. But you can imagine in a future where we have better hardware and more similarity across the different QPUs in terms of noise, you can parallelize that a lot easier. Now, the next example is what we call circuit cutting. And the idea here is that sometimes you cannot implement a unitary channel, the desired unitary channel in your hardware. Maybe because your QPU doesn't have enough qubits, maybe because the topology doesn't allow for the kind of connectivity that the unitary calls for. And one thing you can try to do is to do what is called a quasi-probability decomposition of this unitary channel. And here you will have these coefficients AI that can be negative, and then you will have unitary channels epsilon I, which you have easily implementable in your device. Now, the way you will run this to obtain an execution of the original epsilon channel that you want is you will choose each epsilon I and execute it with some probability that is related to AI. But we said that AI can be negative, so it's not really a probability distribution. It's what is called a quasi-probability distribution. So in order for us to turn this into a probability, what we do is we take the sum of the absolute value of all the AIs, and then we define this probability as each absolute value over the entire sum. This is something that goes from 0 to 1 and is always positive, so it can be used as a probability. And then we have to account for the sign of AI in our expression. But one thing that has happened in our expression now is that we have this gamma that is multiplying the time thing. And that multiplication ends up being an overhead because you are increasing the noise as well of your observable. And what you have to do is you have to sample your circuit by a factor of gamma square more in order to undo that noise amplifications that you have done when you decompose your target channel that you want to do. Now, one thing interesting about gamma is that if you cut your circuit in order to extract the different epsilon i's, if you cut it in a way that you are cutting more than one gate, let's say entangling gates, gamma tends to be lower. So if your cut cuts through 3 or 4 2-qubit gates, that's a better strategy than cutting one and another one and another one in individual cuts. But in any case, you're going to pay the price of gamma to the 2n for n cuts, that gamma being whatever it is for the particular cut. Now, one example is, imagine we want to implement these 2 C0s on the left. What we can do is we can use a bell pair C0, and that bell pair we can cut it and express it as we have in the right. And in this case, we are doing 2 at the same time. And for each bell pair that we cut, we need 2 additional qubits in our system. Now, the important thing here is that if you look at the purple and the pink, they can be separate systems that they don't have any connection with each other. They can be separate chips and separate features. But then you can implement this virtual entanglement through them by doing this decomposition that we have on the right on the separate systems, right? And then the other thing that you need that we are representing here is this classical communication, this is essentially a teleportation protocol where you measure after the entanglement that you have in your local system, and then depending on the measurement, you perform an operation in the other subsystem. So this is what is called local operation and classical communication, LOCC. You can also do something that is only local operation without classical communication by breaking down an entangling operation into separate operations. That can be done, and that will be the subject of the next circuit netting example I will give. But for now, I can show this example where we wanted to implement this graph state in an Eagle processor, but we wanted to do it in a cyclic way. And what we are missing in a planar device is that we cannot connect one edge of the device to the other because we don't have the gates. But we can do that virtually, and we have here at the top left, these 4 blue connections are virtual. Now, we can implement them in several ways, and there is this paper that I have here in the bottom right that does these experiments. And one way is to do swap gates. So basically, you just move the entanglement with a lot of gates through the device to reach the other end. The other is, as I was saying, just doing local operations. So the 2-qubit gates that you want to do, you can express them in terms of local operations in each of the qubits. If you do that in this case, you will get quite a bit more circuits. You will get, I think, of the order of 36 extra circuits for the local operation. The swap gate, you need so many gates that in the end it takes, for this particular case with Eagle, more than 500 extra gates at 1% error. So you can expect the result to be a lot worse for the swap. And then for the LOCC, we get 27 extra circuits, but we need this classical communication, and that could and does, in fact, in this case, incur in some delay, because after you measure, you have some classical processing of that measurement before you can implement the next local operation. So it's a bit slower than the LO only. It's a bit cheaper in terms of how many circuits you have to do, because you need to do only 27 in this case. But here we have some results. What we are plotting here is the eigenvalue of each of these graph states. Not the graph state, but the eigenvalue of the sites. And at the top and at the bottom, we have what we call the entanglement width, W, which is defined in that way, and whose ideal value is minus 0.5. And we see that the swap does fairly poorly compared to the local operation. And both the local operation and the local operation with classical communication, which has also some error mitigation included in this plot, they do fairly well. There is also one result here in red, which is just dropping the edge, which is just simply forgetting about the difficult bonds that we cannot implement, and then doing it that way. Of course, then you cannot do some of the entanglement width that you have in the far left of the figure. And in fact, you are implementing a different graph state. You are not really implementing your target for the problem. So this is included here just for comparison. So another example of a circuit knitting technique that will allow you to run circuits that are bigger than your system is what is called entanglement forging. And this is what I was saying before, that you can take a quantum state, a bipartite quantum state, across, let's say, across two systems, and you can express it as a linear combination of product states that are local in each of the two systems. The coefficients that go with that linear combination are called Smith's coefficients. And these coefficients are such that you can imagine if you only have one of them being non-zero, you have a completely separable state, because you will have a product state that is completely separable, and that means no entanglement at all. If you have maximum entanglement, that means that all the Smith coefficients are the same, and they are 1 over 2 to the n. And so, or 2 to the 2n. And so you have all this distribution there, all this balance between the different Smiths, the composition of your state, and how that ends up turning out depends on what the level of entanglement of the state is. Now, once you have this expression for this state, you can go into the density matrix formalism, and then the expression becomes quite a bit more complicated, but nothing has changed in essence. You still have the lambda for the Smith coefficient, and then you have your basis states for the separable systems. And here we are defining this phi in order for us to express this a little bit easier. And then from here, the natural next step is to estimate how an operator expectation value will look like. And here we have this expression that we can then use to solve some problem. And we have two very distinct parts of this expression. One is when we have the elements that are pure bn's, and then we have some elements that are a linear combination of states in each of the subsystems that are these phi wave functions. Now, we have an example here that was run in this paper where you can take the water molecule, which in principle will have, I believe it is 14 orbitals, but we can freeze a couple of them and end up with 10. So you will have 14 come from 7 plus 7 for spin up and spin down. If we freeze a couple of those, you end up with 5 plus 5, which is 10 orbitals. And here we'll have a circuit that will fit in 5 qubits, and we will run the two systems separate. So here we see that the two results that we have in terms of energy have to do with the dissociation of the molecule in terms of the bond length in both oxygen-hydrogen bonds, and also in the single bond on the right-hand side. And we can see that for the points at which the error is lower, which are the points on the left of the figure in both cases, correspond to the terms with less entanglement. And that's because when you have lower entanglement, it's easier to do this forging, because you are dividing the system that doesn't have a lot of entanglement. You don't have to pay a lot for it. Whereas, as we go to higher error, we see that the evolution has been towards larger entanglement, which means that the SMIC coefficients are more uniform across all of them. So this is one example of something you can do with this entanglement forging, and again, this is something that is still exponential in overhead. Another technique that can be exponential in overhead is what we call operator backpropagation. So what we are doing here is we want to run a circuit that is in size or in depth beyond what our system can do even with error mitigation. So what we can do is if we want to implement this unitary circuit and get the observable O at the end and get the expectation value for that, we can break down this unitary into these two unitaries, U1 and U2, and then we do a classical backpropagation of the observable through U2, and then what that has as an outcome is a new operator O prime, which tends to be typically a lot more complicated than the original operator, and then that's the one that we are gonna try to get outside of the circuit, which is gonna be, now we only have to implement the circuit as to U1, right? So there are two ways in which we pay a price in doing this in this case. One is that our observable O prime, as I said, is going to be more complex. Typically, you want to do this with operators that are low weight. This O initially, if it's low weight, you have a better chance of propagating further. And then the second price is that this evaluation of U2 back tends to be expensive, classically, and typically we will need high performance resources to do that. There are several ways of doing this back propagation. You can use tensor network, and here I'm showing one option, which is what is called Clifford perturbation. So you take the action of each of the gates that you are back propagating on your observable, and normally when you have an arbitrary rotation, that is going to turn your observable initially into a couple of other observables. So every time you do this propagation back, you are going to have been increasing the number of observables by 2 in the worst case. And if that rotation has an angle that is very low or is very close to pi or pi and 2, meaning if that operation is a Clifford, then you don't have a new observable. You just transform your previous observable. So it's a lot cheaper to do backpropagation with Clifford operations than with arbitrary rotations. So the closer your circuit you're backpropagating is to a Clifford circuit, the cheaper this method is going to be. What you can do as well, as we are seeing here, is you can truncate some of the elements that you get. So you can do some backpropagation, and you observe that some of those elements that you get, meaning the new observables that you are getting, they might have a very small coefficient, so you can truncate, you can forget about them, and then keep doing that. And of course, every time you do that, you are incurring some error in the output. But you can have a budget of that error, and for example, here we have this circuit here that we are going to implement k times, and we have these 4 slices that they comprise Control Z and in black, and then we have some other potentially non-Clifford operations. And we know that because the Control C's are Cliffords, we are not going to have an error in those 2 layers. So if our total error budget was E/4k, then because our total budget is going to be epsilon, so epsilon/4 for layer and then times k for the repetition, then we can distribute in this block the error into epsilon/4k and 3 epsilon/4k, or we can try to distribute it equally. But there's a lot of freedom in here. So this operator backpropagation as well, we can see how it also tends to scale poorly, so we only can do it for so long before the amount of of circuits we have to run grows as too large. And also we know that we will need probably to use classical high-performance resources to be able to do that backpropagation. So this fits very well again in this quantum-centric supercomputing vision of having these parallelized workloads and having a part that is high-performance classical and a part that is quantum. Now I'm going to mention a couple of other ones that are very interesting to me. One is a new version of Shor's algorithm. I will give a very, very brief intro of how Shor's algorithm works, and then we can see how the new version naturally comes from it. So the idea for Shor's algorithm is to solve a problem that is given a composite integer to find its non-trivial divisors, right? So the factors of this n, capital N number. So if you consider the multiplicative group of modulo n that we are going to call G. So what is this group? In fact, this group will have all the numbers that don't have a common factor with n up to modulo n, right? So one really cool property of this is that if we take a number x and we a number that belongs to the multiplicative group and we elevate it to the power of the cardinal of G, then we get the result of this 1 modulo n. So we can also say that this is a related theorem that says that x to the p minus 1 equals 1 modulo p, and from there we can say that x to the p minus 1 times q minus 1 is 1 modulo pq. But pq is what we are looking for because, I mean, either p or q, because we have that n equals pq. So if we get this cardinal for this multiplicative group, we will get the factors of n. And so, this is a way that you could solve Shor's algorithm if you have a way of getting this cardinal. And for example, here, if we use n as 15, then this group G will be this sequence of numbers, and then it has 8 elements, which is the multiplication of p minus 1 and q minus 1. I have a typo here, and now this will give us that because we know pq. We know n, in fact, then we can use this to obtain the factors which are 5 and 3, right? Now, Shor's algorithm doesn't give us this number, but it gives us the period of this function, which is the modular exponentiation modulo n. And that period is not the cardinal of G, but it divides the cardinal of G. So in the end, what happens is that you run Shor's algorithm, you get this number s, and then, if s is even, then you can express this as, the difference of squares, and you end up having, something that divides n, right? Exactly. And so, if neither of these elements are multiples of n, then you find automatically the factor of n. Now, it could be that sometimes s is not even. Sometimes n is a multiple of n. S is not even, or this expression is a multiple of n, and in that case the algorithm didn't succeed. But that's not too bad, because with more than 0.5 probability, you will get one result that is it meets this condition, and we will give you a factor. So it's okay to run Shor's a couple of times because it doesn't take many runs to get one of the factors. And one easy feature about this algorithm or about this problem is that it's very hard to find the solution, but it's very easy to test a solution, right? Because it's just multiplying. So the way that Shor will work, in fact, is to do this modular exponentiation here that we have in this circuit, And then it does it for all the elements in this multiplicative group at the same time. And then what you have is you do a quantum Fourier transform on that to extract the period, right? So for example, we run it here for 15 and we use our x. We can choose a random number for our x. It can be 2, it can be 8. In this case, we are using 8. And we have these outcomes in terms of bit strings. So we have transformed the bit string in binary to decimal. And for each of these outputs, we compute this number, because Shor's doesn't give you S directly. It gives you something that depends on S, and for a particular R, where R is any number between 1 and n minus 1. So here we have 4 values, and these 4 values will give us 4 fractions, and from each of these fractions we get an S. So we see that more than half of the time, but in terms of probabilities, we have more than half of the time we'll get a guess for S that is the right one, which is 4. So we do 2 to the 4 over 2, which is 2. So 2 to the 2 is 4, minus 1, 3, which is a factor of 15. So we solve it that way. Now, what is hard about this? The complexity of Shor's algorithm is, in terms of qubits, you need order n qubits, where n is the bit size of the number to factor. So 2 to the small n is the number we want to factor. And in terms of operations, what we need to do for Shor is we need to run the modular exponentiation of all the numbers until we get to capital N, which is the number we want to factor. So we are sure to find the period. So those are, if you do that modular exponentiation in a smart way, you end up having to multiply n-bit numbers n times. And then that ends up being of the order of n square operations, which is the number of gates, basically, that Shor's requires. Now, the new algorithm from Oded Regev was a bit more than a year ago. It was published. It has 2 critical elements on it. One is it takes this problem and it moves it to higher dimensions. And what does it do that? Because when you move it to higher dimensions, then you don't need to do the modular exponentiation all the way until n. You can do it, you do it until 2 to the small n over d, where d is the number of dimensions you're doing. So now your modular exponentiation becomes a lot cheaper. And if you do that right, because you are still going to need to do that d times, if you do that right, then you incur in a cost that is n times n over d, right? And d is the number of dimensions in which you are doing this, which we have here. So that's the first component, go to higher dimensions. The second component is to use very small guesses. So not guesses, but the basis of the exponent. But before we were using this number 8, we can use 2, we can use 4, we can use any small number. And once you do that, then because those numbers are small, you can very efficiently do this square and multiply tricks to be able to do, in fact, this modular exponentiation on the entire system n times n over d times. Now, this d can be shown to be optimal at equal square root of n. So now we have n times the square root of n, which is n to the 3/2, which is n to the 1.5, which is smaller than the n squared that Shor's require. So now we have a solution that takes, rather than n square gates, n to the 1.5. And at the price of having to run the circuit a square root of n times. So before Shor, it only ran once. Now we have to run the circuit a square root of n times. And this is something that also we will do in parallel. This is kind of circuit knitting, because you run all these circuits, or it's the same circuit, but you run it all the times. You can run it in parallel, and then you have all the outcomes of running that. You run it through a classical algorithm that can produce the final result in an efficient way. Now, the problem with this algorithm, or the limitations, are that the number of qubits, the number of gates are lower, but the number of qubits is larger. In principle, you will get n to the 3 halves, because what you are doing now, you need additional registers to write all these other D elements that you are doing in your circuit, versus the original short, which was order n. I think the exact number is 3n for shorts. So this first limitation was addressed by a recent paper, which took it very close to the original source. It's not quite there, but I think it's 15n, but is very close to that. And the other is that this Regius algorithm it doesn't have this theoretical guarantee. Right? There's a conjecture that is assuming in terms of numbers, in terms of the fact that when you multiply these small numbers, you're in fact going to be able to do it in n times n over d. And this was addressed in another recent paper from this year. So this is a nice algorithm, is very promising, but it's an asymptotic result, meaning that, when you think about, how is this going to work for my RSA 2048? Can I use it for that? Well, we don't know, because that's a very specific problem, and calculating the constants for the overhead is not easy, and it's not clear how to do it, so we don't have a clear resource estimation compared to shorts. This work has been extended to discrete logarithms by another paper last year. And it's very interesting, and to me, this is one very important thing, which is even algorithms that have been very relevant for several decades, like Shor's algorithm, they're still amenable to improvements, and they're still amenable to try to put them in these higher vision workflows and try to get a better performance out of our systems, starting from the algorithm definition, not just only at the circuit level. Another way of doing circuit knitting at the algorithm definition is what we call multi-product formulas. Right? And this is another case that is very interesting, because this shouldn't incur in an exponential overhead. So going into what a product formula is, if we want to solve a Hamiltonian, normally what we need to solve is this problem, where we have this equation of motion, and then we have this solution that has the Hamiltonian evolution in terms of this exponential. Normally, we don't have access to this Hamiltonian. It's very difficult to implement in our system, but we can implement the Hamiltonian as a sum of other f sub a here that are implementable with single and two cubic gates, right? So we call these product formulas, and in this case I'm calling a first order product formula, this kind of multiplication of the exponentials of each of them. And because these FA are not necessarily commuting between themselves, you incur in some error, so you can approximate your Hamiltonian with this product formula up to order p plus 1, where p is the order of the product formula, in this case first order, I'm showing here. Now, normally what you do in your Hamiltonian evolution for solving this kind of dynamics is you break down the steps in small chunks, and then what is called a Trotter evolution, and then you do that as many times as you are dividing it by. So you have this rows of k, and then this is what is called a Trotterization. And when you do that with product formulas, you can see that you can approximate your original solution up to this factor here, which depends on the time over which you evolve it, and it depends on the system size n, and it depends on the k, which is the Trotter step, right? And this paper proves this result. Now, if we go to multi-product formulas, what we are doing here essentially is we are taking a linear combination of product formulas, and we are using that as our approximation to the solution. And if you do that, then you need to first calculate these CI coefficients, which is not trivial, but it can be done. And then you have a quadratic reduction in the error, as you can see here. So what we are doing essentially here is a form of Richardson extrapolation. So for different k, for different Trotterization steps, we are estimating the result of the solution to our problem, and then we can extrapolate to 0 by doing average or extrapolation, similar to how zero noise extrapolation works in error mitigation, right? As an example, we can see here, I think this is for a time crystal, some Heisenberg part of the Hamiltonian. So we have a Hamiltonian, I think this is XXZ term in this plot. And we are plotting the quantum Fisher information, which, if things work smoothly, then this should scale with the logarithm of the time evolution. And we can see that, when we have a very, very small throttle step, which is, it's something that doesn't approximate very well the evolution, we have a very large error. As we increase it, we get closer to the real value. But it is when we extrapolate that we get really this multi-product formula outcome. And this is really nice because you have this kind of linear overhead when you are implementing this solution. Right? Okay, so this is all the circuit knitting tools that I wanted to bring up. But I want to end with something that I think is really, really cool, which is a very recent result that leverage a classical supercomputer, which was Fugaku in RIKEN, which is the top 4 supercomputer in the world, which a Heron quantum processor from our team, which is also a state of the art in terms of quantum, in terms of error and capabilities. To give context to this problem and why it was solved, so we are trying to solve a problem for which it was believed that there was no realistic approach to solve before we get to error correction, right? And the reason was that, and this is one of the problems, which is this iron sulfur cluster, which you can try to solve with 72 qubits, which we have in our systems. But if we have it mapped into qubits with some realistic basis set, then what we end up having is nearly 7 million poly operators. Now we need a precision for chemical accuracy of around 10 to the minus 10. So, that ends up being that you need to execute these circuits 10 to the 20 times each, and we have all those poly operators. So if we run each circuit at 10 microseconds, then we end up having 3 million years for solving this problem. So that's not practical, of course. I must say, this is not optimized in the sense of, we could redistribute the poly operators for being more efficient and so on. But eventually, we will have still a very demanding problem when we try to solve this through expectation value of observables. This was done, and here is the reference, with a Heron device and using 6,400 nodes at Fugaku. And the way this works is the following. Rather than getting this expectation value of the observable by sampling the distribution of the poly terms at the output of the circuit, what we do is we express the wave function of the problem in terms of the basis, the measurement basis. And we assume, this is a very important assumption here, that the wave function is sparse in that measurement basis, meaning that there are not many terms in that measurement basis that are non-zero, essentially. Because if you have many that are non-zero, then you will have to sample exponentially in the size of the system to be able to extract that information. So if the state is concentrated around several measurement basis bit strings, then we know that we can sample efficiently around those, and then we will be able to extract information efficiently. So the way you do it is, if you get a set of bit strings that we call SR here, we can use those bit strings to build a matrix element for our Hamiltonian, and then each bit string or each pair of bit strings is going to give us a different matrix element. So the more bit strings we get, the bigger is that matrix that represents our subspace of H. If we sample it entirely, we'll have the entire space. But that tends to be very, very expensive. So even if it's concentrated. So we sample whatever number of samples is practical, and then we end up with a subspace of our Hilbert space for that problem. And then from there, what we have to do is we build this matrix with all these matrix elements from the samples, and then we use a supercomputer, classical supercomputer, to diagonalize that. And when we diagonalize that, we get the eigenvalues, which are the energies, right? And because this is a variational problem, we know that we are going to get, we have a guaranteed higher bound of the final answer, meaning that if we measure energies that are lower by, for example, reducing the error of our system, or by using more samples and having a larger subspace, if we get a lower energy, we know that it's guaranteed to be closer to the real solution than a higher energy. And that's very important. So we have these elements. Another important piece of this is what is going to be the circuit that we use. That circuit essentially has to be hard classically, because otherwise we wouldn't need to do a quantum computation. We could, if the circuit was easy classically, we would just run this on classical hardware, right? And here we are using a particular type of circuit for the ansatz, which is called local unitary cluster JASTRO. And the motivation here is that typically we have two options for doing the ansatz. We can have a physically motivated circuit, which tends to be very difficult to implement. It's very deep, and it has a lot of gates, but it captures the problem very accurately. And then the other way that people tend to do it, which is practical, so that's the way that people tend to do it, is what is called hardware efficient ansatz, where you might not be able to capture the problem very accurately, but you know that the circuit fits very well in your system, in your topology, and you're going to be able to run it. So this is somewhere in between both of these, and there are more details about this in the paper. Now, this is kind of the workflow. We'll have some samples coming out of the quantum system, and then what we do is we do this step of what is called configuration recovery, which, based on some symmetry arguments on the wave function, you can fix some of the bit strings by associating the right number, the right Hamming weight, basically the right number of ones and zeros that each bit string has. And we do that self-consistently. So you will do that, then you will get an energy at the end, then that energy will determine, well, this is going to be the new kind of Hamming weight that I should aim for, and then you do it a few times until you converge. And each of those samples, what you do is you divide it in batches, and you send it in parallel to all your to the nodes in your classical computing, and then from there you get a set of energies, and you choose the lowest one, which is the one that is going to be closer to the real one. So in order to do that, we have here the workflow where we have this mapping, optimizing, and executing steps from the Qiskit pattern, and then here is where in this star is where the information is transferred between the QPU and the classical. And this is one example where you could benefit from a tighter integration in the system, because you start getting samples out of your system, and you can start straight away analyzing them. Typically, I think for the problem size that we are dealing here in this work, we don't need a very, very high bandwidth, probably of the order of 1 megabit per second or so, which is very, very easy to attain. But workflows in the future might need more bandwidth. And then, as I was saying here, we run this configuration recovery, we run the projection and diagonalization, and then you get the answer out. So there were 3 particular molecules that were done with this in this work. One was the breaking of the nitrogen bond, and this is one problem that is very standard in classical compute to benchmark computations or to benchmark systems. Sorry. And here we have the classical best solution here in black, which is the heat bath configuration interaction, and then our quantum is this one in red, and it captures very, very closely qualitatively the behavior of the classical solution. And this is something that, we have a qualitative answer in this problem that is very close and is used in a realistic. This is the first time that this molecule is solved with quantum computer using a realistic basis. Now, the second experiment that we did was one iron sulfur cluster, Fe2S2, and here the idea is to study many body physics. And as you can see here, there were three main eigenstates, that were obtained by this method. And for one of them, if we do the extrapolation, and these different points are obtained by increasing the size of the subspace, by getting more samples, up to the maximum was 100 million samples. So this is 100 million by 100 million matrix that was diagonalized in the supercomputer. Then if we extrapolate these points, we get the result at basically the entire space size. And for one of the eigenstates, we recover a result that was within the confidence interval of the classical state of the art, which is very promising, very encouraging for our systems and how we did these experiments. And finally, we wanted to go to a point in terms of problem size where we wanted to check if there was something the quantum computer was doing, or it was all like the classical computer essentially doing everything. So what we did is we went to a higher size problem, and we tackled this other larger iron sulfur cluster, Fe4S4. And here we're using 77 qubits, and we compare the output of those circuits in terms of the samples from sampling from a uniform distribution. And we will pass these uniform distribution samples to the supercomputer and say, well, you deal with it the same way you will deal with the other samples, and see what energy you get. And what we saw is that the points coming from the classical, the uniform distribution, where first they were not in a straight line, which means that they don't represent an eigenstate. And second, they were a lot higher energy, as we can see in the top right here in the rightmost figure. Which means that in fact we are doing something useful with the quantum computer, even at this size of system. This was not, in terms of comparison, not close to the best classical, but definitely we can demonstrate that we have a signal that is meaningful outside of a quantum system of this size. So these were the three experiments. This is, there is a lot more improvements that we want to do for this workflow in the future, and we are working towards that, optimizing the circuit and so on. But this is a really beautiful example of how a workflow that leverages state-of-the-art classical computers and state-of-the-art quantum computers can come together for a very interesting problem. This is the final conclusions for this particular experiment. These chemistry workflows are going to be very interesting in the near future when we are coupling supercomputers and quantum computers. And in summary, there's a lot to look forward to in terms of how we are evolving HPC into the next era in which we will have accelerators that are quantum, and there will be a lot of interesting problems that start getting developed as we progress in that direction. Thank you. It was great to be able to talk to you.